Hello, my friends. Mrs. McBride here. What we're doing today is we're talking a little bit about Kepler's laws. So, first of all, let's go ahead. And just like Newton, Kepler has 3 laws. Why is it all laws come in multiples of 3? I don't know. You guys, what you need to do is come up with a physics law that is in a multiple of 4. That's your challenge. All right, so what we're talking about is Johannes Kepler. And Kepler was around from 1571, we think, to 1630. So what was going on in the world right around then? Well, it was the scientific revolution. So this is when Galileo was around. He was a contemporary of Kepler. And also the Mayflower was just starting to set sail and on its way over to what would now become the United States. But it was really a kind of an interesting time to be alive. Now, Kepler, what he did is he derived his 3 laws based on the work of a gentleman by the name of Tycho Brahe. Do you remember that name from the movie, the Edpuzzle that we watched on the mechanical universe? So Tycho Brahe basically is a guy that has a lot of money, and he says, you know what I want to do? I want to look at the stars and the planets. So he did all of these very intricate observations of the way that the planets moved based on the sun. He did all of these things without a telescope because the telescope hadn't even been invented yet. And his observations were actually surprisingly accurate, but he didn't really know what to do with them. So he gives his work over to Kepler and says, here, I got this data for you. And Kepler was like, this data is great. And Kepler takes this data and makes it into Kepler's 3 laws. So the first of Kepler's laws says the following. This one is called the law of orbits. And very simply, it says all planets move in an elliptical orbit with the sun at one focus. I remember learning about ellipses as a kid in math and not really enjoying it. Okay, but what this is basically saying is pretend that we've got an ellipse, and an ellipse has 2 different focuses, and the sun is here at one of those focuses. Okay, and this, the distance from sort of the center to here, we sometimes call r. Okay? Now this is important because this helps determine how circular something is. Now if you think about it, Kepler was right, but also not right. Okay, we've always drawn the solar system like this, where here's your sun, okay, and it looks more like this. Is Kepler wrong? Well, this is a law, so we know that he's not. Okay, are we wrong to say that, pretend like these are perfect circles, yikes. Are we wrong to say that all of the planets orbit in a circle? The answer is we're both right. Okay, so Kepler is technically right because yes, you are correct, or he is correct, that all planets move in elliptical orbit. They're just not that elliptical. And we can figure out how elliptical they are by defining something called the eccentricity. And maybe you remember this from earth science. This is also denoted by lowercase e. And basically what we're doing is we're taking the distance between, I'll say it correctly, the foci, and we're dividing it by this r value, okay? And this value is always between 0 and 1, okay? The eccentricity of a circle is actually 0. Oh, you know what? I think I drew r incorrectly. R, if this guy here is r, I'm so sorry. That's the radius. That would make sense that it was r. Oh, come on, Mrs. McBride. Okay, so if you take and divide, if we have a circle, you would think that the 2 foci are together, or you would get r over r, okay? The eccentricity of Earth is 0.0167. So is it an ellipse? Yes. Is it pretty circular? Yes. Okay, so we're sort of both right. So his first law says that all planets move in elliptical orbit with the sun at one focus. Great. So again, the fact that the eccentricities are so close tells us that these are very close. Okay, and again, the distance between foci would be very, very small, which is why this is almost zero. Okay. All right, Kepler's law number 2. This one's called the law of areas. And what Kepler is saying is that planets sweep out equal areas in equal times. And hopefully you remember this again from that mechanical universe video where we saw this in action. Or if we go back to our picture here, here's our ellipse, here's our foci, here's our sun. We're basically saying that as the planet is orbiting around the sun, it's going to sweep out some amount of area. And as the planet is moving farther away from the sun, it will sweep out equal areas in equal times. Okay. And we're going to prove this today in our Kepler's Law lab. All right, last but not least, this is called the law of periods. I don't like the wording of this, but the law of periods is an equation. Okay, so I'm going to skip the words here, and we're going to talk about how do we actually derive what that equation is. Now, the AP Physics C exam says that you need to be able to derive this exact equation. So in class, when I see you tomorrow, what you're going to do is we're going to go over how do you actually derive this, and then I'm going to give you a quiz on this just to make sure that everyone is proficient at this. Okay, so this is derived in the following way, the law of periods. Okay, it's starting out with, in the same way that we sort of start out a lot of our equations, F equals ma. And if we're talking about objects that are moving in a circle, or specifically planets, the reason why they're moving in a circle is due to the force of gravity. Okay. And since they're moving in a circle, we can say that the acceleration that they have is centripetal acceleration. Okay, so from here, what we're going to do is say, well, there's two different ways that we could write out Fg. We could write out our Fg equals mg, or we can use our Fg equals g m1 m2 over r squared. Since we're looking at objects that are not on the surface of Earth, we're going to use this one. Okay, and for my two masses, one of them is going to be the mass of the planet. Excuse me, it would be the mass of the thing that is moving. Okay, so in this case, it would be the mass of the sun, and the other one would be the mass of the planet. Okay, so this is going to give us big G, mass of the sun, times the mass of the planet, divided by the distance that they're separated. And remember, the distance between the Earth and the sun is 1 astronomical unit. Now over here, which mass would we use? Would we use the mass of the sun or the mass of the planet? Hopefully you're saying to yourself, well, I would use the mass of the planet because that's the thing that's doing the moving. That's the thing that's in circular motion. Okay, now how about the centripetal acceleration? Okay, do you remember what the centripetal acceleration is equal to? I think I heard somebody say v squared over r. So this is going to give us v squared over r. Okay, so we can do a couple of things. First of all, let's do some canceling. And, okay, so we're going to get big G times the mass of the sun divided by the radius is equal to v squared. But I'm sure you remember that when we were talking about things moving in a circle, we said that velocity is always equal to distance over time. Well, what's the distance that we travel when we're moving in a circle? I'm hoping you were saying to yourself, that is the circumference, or 2 pi r. And the time it takes something to move in a circle is t, the period. Okay, hopefully you were saying to yourself, McBride, if this is called the law of periods, somehow or another, we better get the symbol for period in here. Remember, period is the time it takes something to make a full revolution. Okay, so if we plug this in here, we get big G times the mass of the sun times the radius. And then on this side, we get 2 pi r over t squared. Now let's do some math here, because all we're doing is from here, we're gonna go ahead and solve for t. So I got big G times the mass of the sun divided by the radius. I'm gonna go ahead and square this out. So this is gonna give me 4 pi squared r squared over t squared. And again, I said we're gonna wanna solve for t. So I'm gonna do a little cross multiplying here to get some stuff out of the denominator. So we get t squared G times the mass of the sun. Remember, you're gonna have to do this. Is equal to, okay, we've got an r times an r squared, which is gonna give us an r cubed, okay? So let's go ahead and get rid of, we're solving for t, this is the law of periods. I'm gonna divide both sides by GMS. And I'm gonna write this a little special way here. T squared equals 4 pi squared over GMS times r cubed. There's a method to my madness here for a second. Okay, and this, my friends, is the law of periods, okay? Where r is the distance between the center of the earth to the center of the sun, ms is the mass of the sun, this is big G, and t squared is the time it takes to make one revolution. Okay, so if we were talking about this, maybe we would say that t, in our case, how long does it take the earth to go around the sun? Maybe you're saying 1 year or 365 days, okay? We would want to use that time in seconds, so that would be the time you would use there. There's another way of saying this though, because if you look at this particular term right here, 4 pi squared over G times the mass of the sun, this is really a constant number. It's not changing. So what you can do is we can write the law of periods a different way. We can say that since this value is a constant, and I bring this over, I can say that the period of something, I'll just call it a squared, divided by the radius of a cubed equals the period of b squared divided by the radius of b cubed. So this works for anything that is rotating around the same thing. So what I'm saying is if I took the t squared over r cubed for Earth, it would equal t squared over r cubed of Mars, because they both rotate around the sun. Or t squared over r cubed of Venus is equal to t squared over r cubed of Jupiter. Since they rotate around the same thing, their t squared over r cubed has to equal t squared over r cubed. The same is true for moons, right? Obviously we only have one moon on Earth, but any planet that has multiple moons, the t squared over r cubed ratio is the same. Let's just add that in. All planets have the same t squared over r cubed ratio. All moons around one planet have the same t squared over r cubed ratio. Okay. So in case you were wondering, this is true. So let's say, for example, I take a planet like Earth, and I'm telling you that it's the distance from the center of Earth to the center of the sun is 15, I know this is not in scientific notation, 15 times 10 to the 10 meters, and the period is 1 year. If I look at my t squared over r cubed ratio, okay, so if I basically take 1 divided by this squared, it's going to give me a very small number, this cubed. It would give me 2.96 times 10 to the negative 34, and that would be years squared per meters cubed. Okay, and if I took a planet like Neptune, and Neptune's distance is, again, not in scientific notation. Sorry, Google did not want to give me this in scientific notation. 450 times 10 to the 10 meters. Its period is 165 years. And I look at its t cubed, I keep saying that wrong, t squared versus r cubed ratio. This is going to be 2.99 times 10 to the negative 34 years squared per meters cubed. Okay, and you could do this with any particular planet in the solar system, and you would find that although they're not exactly the same, they're pretty dang close. Okay, hope that makes sense. Hopefully you're good with Kepler's 3 laws, so let's just do a quick recap here. The first one is the law of orbit, saying that all planets move in elliptical orbit. Okay, totally not circular, but pretty darn circular. We have the law of areas, that planets sweep out equal areas in equal times, and our law of periods, which says that the period, or t squared, is equal to 4 pi squared g ms times r cubed, or t squared over r cubed equals t squared over r cubed. Hope that makes sense, friends. Bye.